We will be starting with mechanics of structures. We have rigid bodies wherein the external force acting on them will cause either a change in position or cause an acceleration to the body as per Newton's laws of motion. But at the same time, we have non-rigid bodies. There, this external force causes either change in size or shape. That is deformation. This external force can be tension, compression, bending, shear or torsion. I'll give an explanation. See, the first and second figure, they are normal forces. First figure, the force that acts normal to the cross section causes an increase in length. Second figure causes a decrease in length. These are tension and compression and they are normal forces. If the force acts along the cross section, then it is shear force. It causes an angular displacement to the body. Third figure shows that. And in the fourth figure, we have twisting force, in which a moment acts along an axis perpendicular to the cross section of the body. And then we have bending. There also a moment acts, and this moment is along the and this moment, the axis of this moment is along the cross section. So in torsion we have twisting moment. In bending, the extreme fibers, you can see the changes. One of the extreme fiber, it is increasing in length, the other extreme fiber is decreasing in length. Then buckling is a kind of deformation only. There also bending moment acts. Here this particular thing is only for slender members. A compressive force acting on slender members causes buckling. So we have discussed each kind of force and the deformation, corresponding deformation. So simple stresses and strain, that is the topic here we will be discussing. There a very important term is stress, will be coming across everywhere in mechanics of structures. Suppose we are taking the case of the cross section of a body which undergoes tensile force. This we can see it is composed of so many tiny particles. And as per Newton's laws of motion, a body that remains in rest should be undergoing net force 0. That is, in case of non-rigid body, due to the external force, only change in size or shape is taking place. So there should be some opposing force that causes this this body that is the net force acting on this body should be 0. This is compromised by the internal resistance provided by these tiny particles, and this is explained by the term stress. Each of these tiny particles will be resisting this external force, and that is internal resistance, which is stress. Suppose the force F is a tensile force F is acting on the body. So each of these tiny particles will be opposing this force by a stress, tensile stress sigma, denoted by sigma. It is given by F by A, where A is the cross-sectional area of the body. Similarly, compressive stress. And in case of bending, I have already explained, the extreme fibers will be experiencing tensile and compressive forces. this is the cross section of a body undergoing bending moment, and we have the extreme fiber experiencing tension and the other fiber experiencing compression, the magnitude changing in this way. So this is tension, this is compression, and we'll be considering the body to be made up of like the, fibers like this, and somewhere this fiber located somewhere here will be experiencing net stress to be 0, and it is that axis is neutral axis. Anyway, this tensile and compressive, so any stress experienced by any fiber located at a distance y from the zero stress axis is given by my by I, where I is moment of inertia, and we will be looking into this in detail later. And shear stress also, if some force P is the force acting, then if this is the cross section and shear force is acting along the cross section in this way, force is P, shear stress is also given by P by A, where A is the area of cross section. And in torsion, the stress experienced is shear stress only. It is given by TR by J, where R usually we will be considering cylinders. That is where R is the cylindrical bodies, and if from center to the distance of the fiber, circular fiber we are considering, distance of that fiber from center is given by R, because at center we are considering no twist can happen, and J is polar moment of inertia. And we have cases where combined loading can take place and a combination of the stresses may occur. And to explain the deformation, we'll be using another term, strain. It is the measure of deformation produced on the material by the application of external load, and in each of the forces we have to consider separate deformations. For a tensile force, what is the change in length produced divided by original length? Similarly, compressive strain and shear strain, if this is a cube, we are considering a cubical body, and shear force is acting in this way, this can displace body like this. So we are producing an angular deformation in such cases, and shear strain is given by tan of that angle. So I will show clearly. After undergoing the stress, the new body is given by red. I think you have now got a clear idea. And superficial strain is change in area by original area. Volumetric strain is change in volume by original volume. Now another important term to be noted is Poisson's ratio. Suppose we are considering a body undergoing a tensile force as shown in the figure. While the length of the body increases, the lateral dimension, you can see there is a decrease in the lateral dimension. So the lateral deformation, or to take into account the lateral deformation, we have coined a new term, Poisson's ratio. It is given by the ratio of lateral strain to longitudinal strain. So these are the symbols we will be using, and some terms are new to you. We will be going into them. So what is mechanism of structures? The deformation due to some forces, we are taking a study of that, and such problems are dealt using 3 principles. First principle is equilibrium. Sigma V equal to 0, sigma H equal to 0, sigma M equal to 0. So I will explain. V denotes the vertical forces. Sum of the vertical forces, net force acting on the body along all the directions, should be 0 for a non-rigid body if it is undergoing deformation due to an external force. Sigma H means the horizontal forces, the sum of them should be 0. M denotes the moment, any moment acting on the body. Net moment acting should be 0. Next is constituent relation. It is an important relation, and actually it is Hooke's law. And up to proportionality limit, up to some limit, any body which undergoes a stress sigma, the strain that it undergoes is proportional to this strain, stress. That is given by sigma directly proportional to strain. And we have some constants explaining this proportionality. And if longitudinal dimension or length is the dimension we are considering, then this constant of proportionality is Young's modulus E, sigma. That is normal stress by normal strain. It can be tensile or compressive. If shear stress is considered, that is angular displacement, then the constant of proportionality is given by shear modulus or modulus of rigidity G. Shear stress is denoted by tau and shear strain is denoted by phi, which is the angular displacement. And if volumetric, that is pressure is applied, if pressure is applied on a non-rigid body, it undergoes volumetric strain. There the constant of proportionality is given by bulk modulus K. So P is the pressure, and we have compressive. Usually pressure causes compression, so the volume is decreasing, minus P by delta V by V. delta V by V. So these are the constant of proportionalities. And the third principle is compatibility relation. Actually, this third condition denotes that deformation can be obtained by integrating strain, or in simple problems we are dealing with, we need a third relation too, such that we can find stresses and strains, and this is given by compatibility relation. And next, stress strain relations. So we have already told up to proportionality limit, this stress is proportional to strain. It is given by Hooke's law, but it is not the practical case. If we are taking, for example, steel, and we are applying some tensile force on it, it undergoes change in length. The length will increase up to a particular limit. This strain is proportional to stress, which is the proportional limit. And we are applying some this is a steel rod, and we are applying some tensile force, and on releasing this force, it will be moving back to its original size. This is an observation we will be seeing while applying tensile stress on a steel rod, and this is only up to a particular limit, that is elastic limit or yield point. After that, this deformation is permanent. That is, even after removing the force we are applying on the steel rod, whatever deformation it has undergone due to the force, it will be remaining as such. So we can see plastic behavior after that. And C is that yield point after which it have a permanent set. So in this way, after that, when we are applying, we are slightly increasing force, it will again be undergoing increase in length, and even for small stresses it will be undergoing larger strains, and this is the way it will be going. And up to D, with the increase in stress, we can see with the increase in stress, strain is increasing. But after D, even after decreasing stress, we can see it is undergoing some strain, and at point E, which is called fracture point, it will be breaking. And this is the relation we will be obtaining for a brittle material like concrete. Stress is proportional to strain up to a particular limit, that is Hooke's law. After that, strain will be increasing as stress increases up to a particular point, and after that it completely breaks. It is brittle material, and steel is ductile material, because with increase in stress we have observed that strain continues to increase. This will take place for some time. Next, these are some terms to be noted. Nominal stress strain curve, it is the curve based on original area of cross section of specimen while calculating various stresses. True stress strain curve, curve based on actual area of specimen at the same instant a force is applied. So there is some difference between, we can see a difference, that is original area and actual area. This is because when we are applying force in one direction, in the other direction, which is the area of cross section, we can observe that it is decreasing. So we have stress defined as force by area. So this area of cross section, we can have original area of cross section before we applied any force, or the true cross sectional area at the moment we are applying force. What is the cross sectional area of the body? That is why we have two kind of stress strain curve. And gauge distance. While a specimen is being tested to an increasing force, a change in length between 2 points A and B on the specimen is observed. The initial distance between the 2 points is called gauge length, and it is given by 5.65 times area of cross section test. And it is just a sample distance we are taking on any body, that is 5. What we will be calculating the area of cross section of the body will be times root of A. It is root 5.65 root A. Then we will be calculating this particular length, and for any cross section we will be taking this much length, 5.65 root A gauge length, and we will be observing the changes undergoing for this particular length, and it is termed as gauge length. Elastic material, a material which regains its original size and shape on removal of stress, is said to be elastic material. Plastic material, a material which can undergo permanent deformation, is said to be plastic material, and this is plasticity. Ductile material, which can undergo deformation without rupture. Brittle material, a material which ruptures with no plastic deformation. The deformation or strain remaining in a body after removal of stress is known as permanent set. And in stress strain curve, we have seen this permanent set, 1%, which is taken as 1%. This is due to the plastic property. Modulus of resilience is the energy stored per unit volume at the elastic limit. This is if we are taking stress strain curve, elastic limit is this point, and at B, if I am taking the area of this up to B, it is actually modulus of resilience. Modulus of resilience, and this area, and it is nothing but product of stress and strain, that area. So that will be giving you the amount of energy lost when it get molded to permanent set, that is up to elastic limit. when we are increasing stress, strain also increases, and when we so area under stress strain graph up to yield point or after up to where it gains permanent set is modulus of resilience. The modulus of toughness is the amount of work required per unit volume to cause failure. That means area of stress strain graph up to now under static loading. Then modulus of rupture is the stress corresponding to flexure or torsion. Ultimate strength in flexure or torsion is known as it is the ratio of stress to strain modulus of rupture, where we will be looking for the point where it breaks under torsion. So we'll be noting that value where it fails under torsion and corresponding ratio of stress to strain will give you modulus of rupture. So there we have a difference. It is known as strength. The modulus of toughness and reliance are energy stored. They are energy stored, but this modulus of rupture, we have a difference. It is the strength or the stress corresponding to the point where it fails under torsion. Strain hardening, the increase in strength after plastic zone to rearrangement of molecules in the material. Due to rearrangement of, that is, I have already told, we have a permanent set. After that, it will be storing itself some energy, which is modulus of resilience. So it has increased in strength as well. That is strain hardening and proof stress. Now proof stress, which is stress corresponding to that. If you are looking in the graph, this is the permanent set. We have the corresponding stress. Is nothing but proof stress. Elongation, we have taken gauge length to be 5.65 root A times root A. Then we fixed a particular percent, that is 1% in the graph. We have already seen it is 1%. So 1% strain, or we say if the stress required to increase the length by 1%. Elastic strain, dimensional change that occur in a material due to the application of loads and disappears completely on the removal of loads. Plastic strain, dimensional change that occurs in a material due to the application of loads and does not disappear after the removal of loads. Now, ductility and malleability, the property due to which we can make steel bars to rods by applying tensile stress, or to plates by applying compressive stress. That is known as ductility and malleability. It is an important property of steel which industries make use of to make rods and plates. And creep in rails due to the sustained moving load of train. Rails get elongated, that is creep. And factor of safety, if we consider some material we are using to yield at some stress 2 kilonewton per millimeter square, we will make sure that stress on the same is not allowed to exceed 1.5, and this is working stress, this 1.5, and this is yield stress. So factor of safety is 2 by 1.5 or 1.33. Margin of safety is that minus 1. Next, before we move on to problems, we need to know some formulas or tips. That is what we are going to discuss. Elongation of bodies. If we have some bar or rod which is subjected to some load P, and due to which it elongates by some delta, then we know by Hooke's law, elastic limit. We know by Hooke's law that stress is proportional to strain, and the constant of proportionality is E, Young's modulus. Stress by strain, where stress is given by P by cross-sectional area A. Strain is change in length by original length. From this, elongation can be given by PL by AE, to be noted. Next, composite beams. Composite beams, if we are considering, we have a material of some cross section A1 joined by another material of cross section A2, again another material A3, and so on, and it is applied some force P. And considering body 3, it should be neutral, remain neutral, so this P will be like this P. And considering A2, we have at the joint A3, that should be compromise P. So body 2 P, again tensile load P, and body 1 again it will be tensile load P. So each will be so A1 will be getting elongated by delta 1, A2 will be getting elongated by delta 2, A3 will be getting elongated by delta 3. Total elongation is delta 1 plus delta 2 plus delta 3. It is PL1 by A1 E1. If the materials are different, their Young's modulus will also be different. P2 L2 by AE2 plus P3 L3 by AE3. This is another important thing to be remembered. Next, for tapered body, that is a body in this way, its cross section is not varying as discrete elements but continuously. So that is what we have here. It is written about composite beams. I will write it again for easy understanding. We have So now we will be seeing the case of composite beams, that is beams which consist of different kinds of materials or different cross sections and all. Here we have a beam, and suppose we are applying some tensile force P here as per and we are going to analyze this. Okay, if we are taking body 1, this is body 2, this is 3, and we have different cross sections for these three as A1, A2 and A3, and their length L1, L2, L3. And as per Newton's law, when we are considering body 1, it is remaining at rest. So if we are taking body 1, we have tensile force P here. For this to be at rest, it should be like this. So in this case, we can apply Hooke's law, and we will be getting delta 1 as P L1 by A1 E. If different materials are used, you should be giving E1. Now if you are taking body 2, similarly P itself is acting. At this area we have P, then it is opposed that P should be here like this, and here delta 2 will be given as PL2 A2 E2, and for the third body delta 3 is given as PL3 by AE A3 E3. So the total elongation of the beam is given as delta 1 plus delta 2 plus delta 3. At this end it is fixed, so elongation is happening this way, delta 1. This body 1 will be elongated by 1, body 2 will be elongated by 2, delta 2, body 3. Totally their joined sections, this join will remain as such. So that is given in this. elongation of bodies, varying cross section, composite beams. Delta L is given as delta 1 plus delta 2 plus delta 3. Okay, and self weight is not considered, means they are discussing a beam hanging from top this way. 1, 2, 3. Okay. Next we have tapered body. Tapered body means its area of cross section is decreasing this way. And we have we have two cases, the cross section being rectangular or the cross section being circular, and we will be discussing that now. This is a tapered bar. See, its area of cross section is decreasing from with the rectangular cross section. It's B into, if its width is B, and suppose width means perpendicular to the plane we are seeing, and this much length. Suppose that to be A. A into B will be the cross section here, and here this will be A plus for easy, if A I am using, you will be confused with area. So suppose I am considering the width to be 1 and this dimension to be small b and capital B. Okay, so we know this much portion we can using similar triangle or principle of slope being the same, we can find this much dimension, like that I will say. We can find the slope also. Suppose the length of the bar to be L. Now the slope, this slope is given by B minus B and two such a section. So B minus B by 2L is the slope. B minus B by 2L, and at any section let it be at distance x from one of the extreme ends. There this length or this height can be given by this slope into x. Two such length are there, plus b. B plus B minus B by L times x. Okay, now for that particular dx, area of cross section is this times width if it is w. So we know the equation for delta for this particular length dx can be given as P if some tensile force P is applied and this end is fixed. P times dx is the length we are considering divided by this area times. So the total, this is for this length dx. For that implies total deformation can be obtained by integrating P dx by b plus b minus b by L times x w times E. So that equation only there they have written. And if we are considering cylindrical, suppose we are considering cylindrical tapering, cylindrical body which is tapering in its cross section, we have at any section taken, or we are considering a particular small length dx at length x from one of the extreme ends. There, if small diameter, the smallest diameter is d and the biggest diameter is capital D, at any section x distance from one of the extreme ends, it can be taken to be d minus d by L times x plus small d. And for area, it will be pi times this d minus d by L times x plus d square. The total deformation can be taken to be integral P, and this is fixed, P dx by A is pi into d minus d by L times x plus d whole square times E. So this will be giving you some equation. So they are discussed here. Tapered body will be getting the deformation, total deformation. If cylindrical cross section is considered, it is nothing but 4pl by pi E times d. And if we are considering rectangular cross section, it is pl by E, and the width, if we have taken it to be w, into b minus b log b by b. Sorry, this log b by b will be pi by 4 is there, okay, pi by 4 d square, that is why 4pl by pi d times E. And here it is 1 by x only, 1 by x integral integral of 1 by x dx will be log x. So log b plus b minus b by L times x to be integrated from x ranges from 0 to capital B minus small b by 2. So that will be giving you this equation. Okay, that is 1 by x. That will be giving you p times log b plus b minus b by L times x. Okay, log 1 by x, integral 1 by x dx will be what? Log x similarly, and there x is ranging from 0 to b minus b by 2. If we are substituting that, log b plus b minus log b, it will be giving you log b plus b minus b by L times x is what? L, 0 to L, then b minus b, so it is capital B minus, sorry, x is ranging from 0 to L only, its value, that height only is varying from 0 to b minus b by 2. Log b minus log next case x is 0, so log b, that will be giving you log b by b. Similarly, for the case of circular, it is 1 by h square, it will be minus 2 by x, that is 1 by d minus d by L into x plus d, where again x is varying from 0 to L. So 1 by d minus d plus d will be giving you capital D. 1 by d minus, next case x will be 0, so 1 by d. It will be giving you d minus d by capital D small d. This d minus d will be cancelled out and will give you because 1 by a h square is minus a h square is minus 2 by x times 1 by a. So here again we have some coefficient for x, that is d minus d by L, and that d minus d, this will be cancelled out, giving you that equation. Next is due to self weight, elongation of a uniform rod due to self weight, and that is we have a rod hanging from a fixed section and the force acting downward is nothing but its weight W. due to which it will be elongating by some delta. This can be calculated by taking similarly some section of length dx at distance x from bottom of the rod. So its area is constant throughout, therefore we can take it to be width into take it some a itself, and you know delta of this small portion is p dx by a e, where this p is weight of the portion below this section. That weight only it is making it a hang. It is nothing but W if the weight is varying throughout the length uniformly. So it can be written to be W by L into X, I believe. So this P can be replaced by nothing but W X by L. So for getting total elongation, you just need to integrate this, which will be giving you W x square by L AE, where x varies from 0 to L, x square by 2 L AE. So substituting that, we will be getting W by 2 L AE times L square minus 0, which is nothing but WL by 2 AE. That is equation given here. Now so we have seen elongation of a uniform rod due to self weight is WL by 2 AE. Similarly, elongation of a cylindrical rod of diameter D and length L due to self weight is given by, I will show you WL by how that formula is derived. That is, they have taken density to be some value, density of the rod to be some value, then WA can by A can be written as that density times length, that is density, if density is given by rho equal to W by volume, volume is area times length, here W by and W is rho G, so rho G A L, rho G A L square, A and A cancel, 2E. This is one way to represent, that is rho G L square by 2E is one way to represent this elongation. And we have one more thing to be noted, that is conical rod. Conical rod is similar way. If we are taking, suppose we have a conical rod with the diameter D at the support and some due to self weight, what is the elongation delta at some section at a distance x, we are considering dx length, sorry, we are considering length to be dx, then rho then elongation delta is given by integral of what weight, self weight Here the load is self-weight, that is weight below this section. That is density times volume is given. For a cone it is given by pi, then r square. R square, some r square, length is L dx by AE, area at that section. It is nothing but pi at that. One by 3 is also there. Pi at that, and pi times radius at that square times E. So if we are cancelling this, you will get it to be rho L square by 6E. So this is the thing to be remembered. Next, okay, with that I am completing this portion, that is finding elongation. And now we are moving to another important section, that is strains, volumetric strains. Until this time we have seen the longitudinal deflection or elongation. Next we will be seeing strains. Volumetric strains is something you have to note about. That is volumetric strain. I have already told for volumetric strain also Hooke's law can be applied. There it is given by some constant of proportionality, considering it to be G, not G, bulk modulus. For volumetric strain it is bulk modulus, and it is represented by, we have used the symbol K, is given by pressure on that divided by the strain, volumetric strain. Now this volumetric strain delta V by V, we can also find another equation. It is product derivative of a product, this delta V. This delta V is derivative of a product. It can be written as LB delta H plus LH delta B plus BH delta L, dividing throughout by V, that is delta V by V can be obtained as LB delta H by LBH, volume is LBH only, plus LH delta B by LBH plus BH delta L by LBH. From this you will be getting it to be what delta V by V can be obtained as delta H by H plus delta B by B plus delta L by L. That is what I wanted to say. Volumetric strain. Next, that is for a rectangular bar. Now if we are taking similarly the case of a rectangular bar or some cuboid, if we are taking the case of some cylinder, you can see cylinder volume is given by pi d square by 4 times height. So there what it can be pi by 4 if I am taking, there delta V or derivative is given by 2d delta d times h plus d square delta h, dividing throughout by pi by 4 d square that is, if you are taking delta V by V, pi by 4 will be cancelled out, remaining we have d square h. It will be giving you 2 delta d by d plus delta h by h. Next, that is for cylinder. Similarly, you can derive for other things. Now we have, when temperature of a material changes, there will be corresponding change in dimensions. Temperature stresses are induced only if the deformations are prevented. That is, if I have a bar this way and I am increasing temperature, it can elongate in that direction. Whatever change happens, it is free in this point. Suppose we have, that is self weight, we have already seen. Due to self weight, some force is applied and it is free to elongate. Suppose we are fixing both ends this way, or in the other case as we have seen, fixing both ends, self weight, it is not free to elongate. In that case what happens, some stress is induced. Okay, so how that can be included, I will tell that too. Suppose here I am giving some temperature change delta T, then elongation that would have happened if it was not fixed is alpha delta T times L, if L is the length, where alpha is the coefficient of temperature change. Now if that is so, this is the delta L term. This delta L term can be equated to this delta L term, and we know some stress. I have already said that some stresses are induced in the bar. It is if that is given by sigma. Now, if the stresses induced are sigma, induced in the bar are sigma, then due to that stress, elongation induced is sigma by E. Sigma by E. Sigma by E times L is the delta L that would be produced. So, the net elongation produced will be 0 if both ends are fixed. So we say that these both are equal, or sigma by E is equal to alpha delta T in case both ends are fixed and no elongations are expected to occur. Now next thing is compound bars. So compound bars, we have already seen composite bars. Two or more materials are fixed in series. Here compound bars in that case we have a rod inserted into another rod, or we may say they are connected in parallel for convenience. Or I will show that the cross section. If we are taking the cross section, we can see one material 1 inside and material 2 outside, and if both ends are fixed, as we have seen earlier, see, we have two such materials, and suppose ends are fixed, stresses induced in both the bars will be different, and we require the elongation also to be the same, since both ends are fixed. Delta 1 to be equal to delta 2. In compound bars, we require delta 1 to be equal to delta 2, and the force or the force experienced, they are actually distributed over both the bars, that is P1 plus P2 is the total, and we have stresses as sigma 1 and sigma 2, and we may come across problems with the temperature stresses induced in compound bars. Therein the problem is we have alpha 1 delta T L to be the elongation or of the first bar that may occur due to temperature stress, and alpha 2 delta T L for the second bar. And the stresses are different, sigma 1 delta, sigma 1 and sigma 2. The elongations due to this will be sigma 2 by E1, E2. So what we require is these two, the sum total of this and this delta L, this net should be the same, net elongation or whatever. Next, they have hinted about hoop stress, that is in the syllabus. Okay, so hoop stress here, actually it is the stress that a cylinder may experience circumferentially. If I am taking the cross section of a cylinder, this is the axis, so that is perpendicular to the plane I am writing, and we have radial stresses this way. The stress is exerted on every particle of the cylindrical wall, that is radially, that is hoop stress. And internal diameter of steel tire, what they are meaning is, actually we will be we know the conventional practice of inserting tubes into tires by heating and all. By heating, there happens an expansion in the diameter, taking advantage of which we can insert the tire, and after this after cooling, it will remain tight inside the tube. So that principle they are hinting here. So what we need is how much temperature change. Their questions may come like how much temperature change should be induced so that this tire can be inserted in. So what we have to do, how much dimensional change occurred with that temperature, that we can calculate using all this alpha, delta T, L and all. So corresponding elongation or change in diameter should be calculated, and that much so we should compromise whether both compromise. We should check whether both the temperature change, a diameter change due to this temperature compromise. And next we'll see that in detail when we look in the problem. So we are moving to problems. That much is the syllabus with introductory part of this subject. And the stress is actually now prove stress, which is stress corresponding to that. If you are looking in the graph, this is the permanent set. We have the corresponding stress. Is nothing but proof stress. Elongation we have taken gauge length to be 5.65 root a times root a. Then we fixed a particular percent, that is 1% in the graph. We have already seen it is 1%. So 1% strain, or we say if the stress required to increase the length by 1%. Elastic strain, dimensional change that occur in a material due to the application of loads and disappears completely on the removal of loads. Plastic strain, dimensional change that occurs in a material due to the application of loads and does not disappear after the removal of loads.